everybody. My name is Jeff Wagner. I'm a Senior Technology Consultant at FMX. And here today I'm going to be covering Houdini 17.5 in approximately 38 minutes. And I don't have a hope in hell in doing that right now. So I got tons of stuff. I'm going to leave some time at the end for question and answers and see where that goes. But just to raise a hands, who here is working professionally using Houdini? And how many are students? And how many would consider yourselves to be advanced Houdini users? Okay, good. Because I'm going to be doing a lot of hands-on stuff. So the advanced guys, there's going to be some stuff in there that you can pick up. But I'm generally targeting this to intermediate users, those users that can add nodes and work with them. But hey, if you don't know how to add nodes in Houdini yet, this is a great example to see how to actually construct networks. And I do everything pretty much live, so sometimes I fall, sometimes I'm good. So, let's go ahead then, and let's see where we're going to go. So this is top 5 features in Houdini 17.5. So of course I have to start with 7. And we did a lot of work on the network editors, and we'll be covering that as we move forward. But one of the things that we have done is utilizing these middle mouse and right mouse outputs. Many times in 17.0, now that we're using these multi-inputs and multi-outputs on the nodes more and more, we can now query the inputs and outputs using the middle mouse button, and we can also take a look at the actual node itself. You can middle mouse on the interface on the node itself, and you get some more information. And let's take a look at that. And here's another example of using the subnets, but this time we're actually using the middle mouse button on the outputs. So those people that use middle mouse to actually add operators, to insert operators, I'm sorry, that's being hijacked by the middle mouse button to query the various different outputs. This makes a lot of sense when we start looking at the various bullet operators and they with their multi-outputs as well, especially when they have their constraint geometry and their proxy geometry. It's really easy to see that. And again, there's also a really nice menu that we'll be taking a look at. So if you right mouse on the node, you'll get this new option called Output for View. And from Output for View, you can choose which output you want that node to display all the time until you change it the next time. So that's a pretty cool feature. I like that one. Flip, number 6. I can't ignore Flip. There's been a lot of improvements inside of Flip. The first one is we've added a condensate solver. And what the condensate solver is really meant to do is to get away from using pop cling. So we finally divorced ourselves with pop cling. And the solver in here is a fairly interesting VEX solver. It's only a few lines of code, so it's very accessible, but it is its own solver. It's a thin film solver. And I thought I'd give this a go inside of a fresh file so we can all see that. So as always, we have this test geometries. If you're new to Houdini, we have these test geometries that we use all the time. And in this case, I'm going to put down the rubber toy. I like abusing the rubber toy all the time. And it's called test geometry for a reason. It actually has these difficulty levels. In this case, the Flippy is considered to be hard all the time. So. And you'll notice that I'm always using the technical desktop. Now, there is this build desktop, and all the tutorials are set up to use build desktop. And even though the build desktop now has this tree view, the tree view actually shows Houdini as an actual path system. It actually is directories in there. And I really do enjoy using this when I start building up more complicated systems. But more importantly, it comes with a built-in spreadsheet, which I'm going to stow now. Now Flippy, and this is another big change we made in 17.5, is we've now basically gone on to secure selection. That means if I want to select something in the viewport, you have to hit the S key. And now when you hit the S key, you can actually temporarily go into a select state. And if I do that, you can see here that Flippy is comprised, as always, of many different pieces. And we all know about the Boolean SOP now, so let's just add a Boolean to fix them up. I do this almost all the time. Where is that machine to learn this? But anyway, so the Boolean does that. And now if I hit the S key and I double-clicked on it, you can see it's manifold now. And that's good. Now what we want to do is taking a look at, just go here. And so we're going to now go and use the condensate solver. So it's really easy. It's under the particle fluid tools. And as we know in Houdini, we split left and right. The right tends to be where all the solvers are. And we have a condensation solver. Pretty easy. You just basically press the condensation solver, selects the object to do that on, and you hit enter. And this builds a simulation whereby we can actually see the fluid solve now. Many times when I'm working inside of Houdini and I'm using the shelf tools, you really want to use this tool up here, which is called hide other objects, ghost other objects, or show other objects. Default is ghost. I like to do hide just so I can see what the solver is doing. And you can press forward and you can see that on top of Flippy, there's actually now some condensation that's forming on him and running down. And we're actually using the pop fluid sop, which got added in Houdini 17 as part of the Vellum editions. And it's actually using this new adhesion force, which is all here. You can actually see there's a wrangle that's exposed that allows us to actually, refit and repurpose the condensation as it goes. And pretty straightforward. But the interesting parts is always the case with Houdini. If you're somewhat new to Houdini, right now we're in this dynamic framework called dynamics, which we also call DOPS. But all the good stuff is actually happening in the geometry context, or SOPs. And if I see here, if I stow my auto deck on the left-hand side, you can actually see there's lots of SOPs up there. So if I hit the U key, I can now go inside the fluid particles node. And how do I know that? For those of you who are a bit newer to Houdini, we actually have dependencies. We can view the dependency links as well. If we hit the D key, we can actually see, we actually have dependencies. But I'm going to dive inside the fluid particle objects, or pardon me, go up into the rubber toy. And look at this mess. So what this shelf tool did is it took our flip object with the Boolean and added a ton of nodes. And that's a big, as you guys know, the shelf tools are great at doing that. They're great as a way of teaching you how to do these various tools. Just lay that out with the L key and pull these up, and now we can see exactly what this tool has done. So it's really breaking it out into 3 pieces. So we have a collision source with an attribute create that actually has the DOP path associated with it for fetching things, and then we have a file cache which actually generates the cache for the collision geometry in case it's deforming. We anticipate that things are going to be deforming. In this case they're not, but we do have a file cache in there. And then finally there's the VDB colliders for the actual fluid to run along. So we are actually now colliding against the VDB surface. And over here we have, create the droplet points. So basically we're generating some seed points. Let me turn the points on so it's going to seem easier. Turn the grid off. And these seed points, you can change anything you want. Those points can be from anywhere. And then we add some attributes to them. And this attribute, for instance, is now adding this emit frame attribute, and it's got a min and max value associated with it. So attribute randomize, again, going to the spreadsheet. So we're just creating some random attributes on the emit frame. So different frames for the emission. And this is used by the solver. We got a fade option as well that actually adds a fade attribute to fade those attributes on and off, or off, I mean. And then finally we scatter some source points to actually emit the surface from. So these seed points, we'll then use a p-scale radius to actually grab some points around it and then motivate these particles as they go down. And then we just attribute transfer these seed points onto the gross points, and then we go out from there. And that's pretty much it. And then you can go into the solver. Actually, we go to fluid particles. And sometimes I like looking inside of here and just seeing the particles themselves, the fluid themselves. And as you can see, we're surfacing the fluids on the fly as well. And so finally we can create objects with some nice condensate. What this is really good for as well is if you need to slide mud or other sorts of things on your characters as you rip them apart. It's pretty easy to do that stuff now. So that's the new condensate solver. No more reliance on using popcling. And let me go back. And the next thing we want to take a look at in 17 is narrowband. Narrowband is a bit hard to demonstrate right now, but we can provide cutting planes on a lot of these. Basically, any particle fluid or any pyrosim, we can slice these fluids up. We can do slice along. We can slice our fluid, and we can select our particles to slice along there. If I actually go in here, and we can actually slice the particles in here, and it creates a slice plane. And once we create these slice planes, we can create T-intersections in the order that we do them. Then we can just simply go into we can basically just press this button, distribute particle fluid, and it will automatically start using HQ. So if you have HQ set up on your render farm, you can immediately start distributing this simulation on disk. It truly is that easy. Setting up HQ takes some time if you don't have that set up. And we do support other render queue managers, but HQ is supported out of the box. So I'll show you some examples of doing distributed fluid. And so we have distributed white water. As you can see, it's much faster and much more efficient. So, And here's an example of some early tests that we did with both the water. It's cut in quads, so it's basically distributed with the white water as well. And some more examples of Flippy going through a tank. And then, yeah, so there you go. So that's pretty straightforward. Great feature. So I think I'm getting into the 5s now. Yay. So UI improvements. I'm going to start off with the Python states. And let's go File, New here. Python states, I'm finding that very few people are actually, even though me telling everybody to look at Python states, a lot of users are not yet understanding or grabbing into Python states yet. What Python states allow me to do is to build a UI interface. And the Python states do have a home in the interface now. If you go, again, I'm in the technical desktop, I have this convenient pane in the bottom. I can open this up and I can choose a new pane tab type. And then here we actually have a viewer state browser. And the viewer state browser, if I open this up, I can now see all the current viewer states that are currently loaded inside of Houdini. Viewer states as of Houdini 17.5 no longer need to be bound to a node. And they allow us, and they give us a way of interacting with the viewport, where we write the code. We can write our own Python with PyQt bindings, and you're going to see a lot more tools in the future that are using this. One that actually does use that is the stroke SOP. So if I go into the viewport and I type in stroke muscles, let's put down some geometry, dive inside of it, and now I can type the stroke. I can now start stroking, and this is all this Python state. You can see it's got a nice geometry handle, so we're limited to Houdini geometry types and a few primitives, but we can have any number of parameters on this particular node working with our state SOP in all at the same time, and same thing, I can write to any number of parameters from the state to the node, and I control exactly how many times that updates. And if you right mouse on the stroke, you can actually go edit, and here you can actually see the Python code. And of course, you can now start editing the Python code. And yep, it's our basic IDE. I know there's always requests to have a better IDE, so do I. So you can always hit Alt-E, and Alt-E will then fire up your favorite IDE. In this case, it's Notepad. Yeah, I had to strip my entire environment. I'm sorry, but I usually go into Vim. So because I want to hide a lot of stuff. I can't show you everything. But so this is your state. So if you're familiar with Python, and you're building digital assets, or you want to build a state inside of the viewport, for instance, that maybe moves two objects around to align to a solver, that can all be done with a state now, and you can own that. So that means if you've got juniors coming on board, you can give them a first-class experience, similar to the same experiences you get in other packages. So it's for instance, there's static methods. So lots of examples for you guys to chew on. As you can see, also the 3 RBD constraints, which we'll be looking at shortly. So an RBD paint as well, stage manager. How did that get in there? I won't talk about that. So, as I said, so definitely check them out. The help is in $HFS, Houdini Python states. And as well as I said before, you can start digging in here. And anybody that knows Python knows you're going to be ripping through the code anyway and trying to figure things out from scratch anyway. So we also have a second thing in here with this GPU accelerated volumes, which are pretty cool. So I'm just going to have a look at these now. So big change in 17.5 is we've now moved to volumes that are ray traced. And it's done through OpenGL shaders, so it's very accessible for customization. It's also faster than using the old slice and dice method that we're using and running standard shaders, so it offers you a lot of control. Plus, as I said before, light extinction is now handled properly as being a ray trace shader. And here's an example that Scott Keating did for the launch, where he's got just a whole smorgasbord of various volumes that are looking forward. And again, just using simple volume collisions. And like everything else, you should be able. And another thing that we did is, if you're in Pyro now and you go to wireframe, finally we fixed the bug that now allows us to actually see the constant tiles that are being consumed by the current simulation. So all of a sudden, it feels faster, even though it's not. But it is a partition sim. So I thought I'd just do a really quick thing of that. So if you're somewhat new to Houdini and you don't even know that we can do clouds, yes, we can do clouds. Again, I'm going to do the flip or test geometry. Let's do just like the rubber toy all the time. And we have a cloud tool, cloud effects. So whenever you're getting a new release of Houdini, you hear a new feature, these sorts of things you should be able to just whip off to just test stuff off all the time, be comfortable with the software and be able to just jam with this and go. The problem with we've got the cloud tool is we know it bakes in the cloud light, which is great because it's a specific operator that takes a look at all the, you define lights in the scene, and then, or you build your lights as point representations on your, and then you can pre-light the clouds. But in this case, I'm going to completely ignore that. And I'm going to blow away the sunlight and the skylight, and I'm just going to put down a point light. So, and lo and behold, now you get your light viewport. So it's that easy. So as high resolution as your volume is, let me go to the cloud object. And whenever you're dealing with these networks, each node contributes something to the scene, and we always start with these things called generators. This particular generator is just basically fetching some geometry from another object, which is the polygon manifold object, and we do a cloud object. And it's got a uniform sampling diff, so let's set that to 150 as opposed to 50, so we get a nice higher resolution volume. And I'm not going to do the cloud light. Why did I do that? But I need cloud noise. And now we can actually go to this light, and we can actually increase its exposure. And then we can move it up. So it now gives you much, much better volume rendering. And of course, now you're all asking, where are the deeps, where are the high resolution, where's the open shader network? Well, maybe those things will come. But for now, we actually get a much faster interactive way of working with lights, which I really enjoy. And the next thing we want to take a look at is, I think, viewport shading. So if you've got a sophisticated model and you've got a lot of lights on it, the one gotcha we have going from 17.0 to 17.5 is we've now added an albedo multiplier. Historically, our mantra principled shader and the way that we do the BSDS, we had this doubling multiplier internally that made our shaders always look a lot brighter than all the other software out there. So we finally combed through all the shaders and also in the viewport, and we cut the albedo back in half. So just be forewarned, and we set that option on, we set that parameter on by default. But we got some really good looking work now, inspired by obviously games. You know, this need to see much better visualizations in the viewport. We've gone ahead and started tackling this project as well. And you can see here there's a comparison between, let me go back here. And we can see there's a comparison between Mantra and our viewport shading, and some examples between the other software applications that we were comparing this to. And we also tested it against all the standard renderers, RenderMan, Arnold, Redshift, just to make sure that albedos were in the right ballpark now. So now you don't get these blown out renders all the time inside of Houdini. And another example of Houdini. And so really nice. And these models are courtesy of Akira Sato. If you don't know, he's got this amazing kit bashing technique where he can build these really sophisticated robots and mechanical things that are just so organic and sexy. All procedural as well. So, and of course we support transparencies as well. So, and so I'm really liking that. So the viewport has seen a lot of improvements. Look for even more in the next release. And now finally we're at Vellum at 4. And Vellum is continues on to be worked on. One of the things that we did is Vellum per point friction. So we asked John Mariella to give a demos for SIGGRAPH, I mean for our release in Montreal. And here he just painted some friction on his clowns. And so finally Vellum has friction. I mean it was a missing in Houdini 17.0, but now it's supported by all the various Vellum objects, from points, the wires, the hair, the surfaces, as well as the tet meshes now all support friction. So, and we'll take a look at another example of this. So here's another example of just painting friction on a surface. And it's pretty accessible. If I go into here and take a look. So this is just a simple example file where I just paint some friction. And let's have a look. Pretty simple example. Again, these are the sorts of files you guys should be able to rip off in no time whatsoever. So we have a grid, and we just add an attribute expression. In this case, I'm adding friction and dynamic friction. So those are the two key attributes that you need to use for Vellum. No different than it is for the other solver, the solid solver. And so I have one grid here that's going to be my cloth object, and then here's my collider. So I've got another grid, and I do an attribute expression on the friction, dynamic friction. And you can see here I just got an at py times 2, so I'm basically making it vary on the y, and the other one's varying on the x. Just put it through a Vellum cloth into the Vellum solver, and there you go. And now you can see we can apply friction to both the colliders and also the emitters. That's the important point to take away from here. So, and the next thing I want to take a look at is going back to Vellum. we have this thing called fiber constraints now. And what fiber constraints are is keeping up with what our solid solver is doing. And so we've added this material W attribute that allows us now to take any directional attribute and use that as a fiber constraint. So with this, you can now do some preliminary muscles. You can fire these constraints, so you can actually create twitch and movement, or you can actually do real movement as well. And all you need to do is just create a vector field. When I'm doing this, the tool that I basically use is, I like using the fur tools, believe it or not, because they generate nice vector attributes. Or you can use the comb tool, the comb surface attributes, and use these to blend in and out. And it's basically just it's just a couple parameters to do this. And we showed some examples of using the fiber groom. In this case, this is an early example of the muscle tool that's not shipped yet, I don't think. And so it's just a way of just generating a flow field. And then we can use that flow field to distort the geometry. And in this case, the flow field is now being used directly by the vellum solver. So you can create these really cool organic shapes. And yes, you can fire things to go up or down or to flop or do whatever you want with it. So there's an example of that. And I might have time to, we'll see if later on if I have time to actually do it. And of course we have the frog race. And this is using vellum friction, yay. So vellum friction with, and the big thing here is we're converting, so I think the big thing here to take away is we're now using tet meshes to do volume preservation of all your vellum objects if you want to do solid objects. It's quite fast and quite efficient. And we sort of pushed back a bit from struts. So struts are still there on the shelf, but we sort of pulled back a bit on them and using these sorts of techniques. And we can just have a quick look at that. So just put down, let's actually use the pig head now. And if I move that up, I won't move them out actually. I should stop doing that. Go inside of here and then just move them up. And so now we can just turn them into, from the shelf tool by the way, if we go to the vellum solver, you can now see that we have vellum tetrahedral. And you can still see that the struts are still there. And we do that, we now create a tet mesh for our pig. And we have the whole setup to do the low res driving, the high res, and then you can press forward. Actually, I should put down a collision plane. And then you can see it hit the ground and flop around. So it's very easy to create these floppy objects. And there's there's a few tutorials on there how to take it, drive it via animation, and do all kinds of things. And then you can sort of paint fiber direction on top of the pig head as well. And as we saw before, the shelf tool adds a lot of nodes inside of the object to actually prep it for use inside of the solver. And of course, we just read these nodes like a book. And you can see that we got a remesh node that remeshes the topology, and then we do a solid conform, which actually is the new tool that actually builds the tet mesh for us. And then we do a distance constraint to build the constraints for the solver itself using vellum constraints. And then we have some more volume constraints that actually builds the tetrahedral volume constraint. There's a request to actually have all of this stuff in some sort of a master constraint, so where we're considering improving the workflow inside of our vellum objects in a way that doesn't break backwards compatibility, but then we get the transform velocity on top of our original pig head, and there you go. So it's a nice framework to start to work and continue on working, so it's really accessible that way. And let's go vellum. And also okay, that's good enough. And now for the new modified SOPs. I consider this to be number 3. It's all over the map. And there's a really cool file. I want to do, and in one of the Illums, I want to actually show, so we've got some ways of building tests against previous release and current release, so we can build these really cool lists automatically. So I've created a simple list of all the SOPs that were, that were new, that were removed, that were modified, and actually had a version bump. And also verbified SOPs. So as we move more and more towards an environment where Houdini can run decoupled from its own UI, We actually have, we're verbifying more and more of the nodes. And for those that don't know what verb nodes are, they're nodes that have been combed and separated into three parts: the UI part, the dependency part, and then the actual code itself. And for instance, the PDG, the procedural dependency graph, can actually use compiled nodes directly as Python calls. So we can actually call a verbified SOP as a Python in a Python call and create and basically use SOPs completely separate from Houdini if you want. It'll grab an engine license though. So attribute string edit, cluster, convert, ends, file, measure to. Measure, remember, wasn't compiled, and that killed us when we were building environment assets that used measure all the time to build curvatures and stuff. So now it's compiled. That's awesome. Volume is also compiled, and watershed. So you know, there's some really cool, and primitive was compiled in 17.0, so that's really good. But some of the new SOPs that I want to focus on is the fuse SOP. So let's go, might as well stick with the pig. Let's go up here and pull him over, and let's put down the new fuse SOP. So it's a fuse 2, and what we can use that for is we can now start fusing points. And in some ways, you can sort of use this to decimate geometry. And let me go here, and let's turn off least point number. And I'm going to scatter some points on it now. Let's scatter quite a few points. Let's actually scatter 100,000 points. And now we can go to the fuse. And the fuse now is fully threaded, and so you can see how fast it is now. So, and it also replaces a couple other functionalities as well. It now, I can actually turn off the output positions, and I can turn on the radius attribute, so I can actually drive a p-scale attribute if it's present on the input. So I can actually have a p-scale now drive the fusing ratio, so opens that up a lot. We can actually match an attribute name if we want. And we can keep the fused points if we want, but they will have an attribute. So if you keep the fused points, what this now has is we now have an array of minimal distance tests as well. So we can actually use this as an alternative to using PC lookup to find out how near or far the points are from us. And we can actually even snap via attributes. So if we even have an attribute on our geometry, any arbitrary attribute, we can use that to snap the points as well. So very, very powerful tool, very open now. And it can actually snap based on groups as well. So this has now gone from just a basic node to something that is really cool. The only thing it can't do is unique points. So we probably have to address that very soon, because you have to use a facet SOP these days to do that. So fuse is much, much faster. And I'm going to now go and also want to take a look at the measure SOP. So, and this is, I'm going to put down the test geometry. Let's do the shader. Let's do test geometry rubber toy. Now, measure is one of those tools that everybody uses for everything that we do. And so the measure SOP is now completely improved dramatically. And Fiona did a really great video for GDC. But the biggest thing for me is now I got points. So the old measure SOP, you had to find out where did it get put in, the detail attribute, to get it put in primitives as points, and you were always stuck. But now we can choose whatever we want to put it on. And we can measure perimeter, area, volume, centroid, and I've got some feedback on centroid. I've heard that's very, very accurate. So you can really lean against this. And the most important use, of course, is curvature. And now we have a brand new Gaussian feature. So you could use this to do anything with a dot product with the normal, to do shading and dirt. And as we know these days, a lot more work is being done now on the high resolution geometry, and less reliant on shaders these days, because if you're running simulations, you can't run simulation on a displacement map, but you can run a simulation on the actual surface itself that is modeled that way. So we're seeing more and more intensive, very high resolution meshes being simmed inside of Houdini via Vellum and our solid object. And so being able to measure that high resolution geometry and do data with it is very important. Another thing that's really cool is the mean, and also principal. So we can do directional based. So if we go to mean, we now actually have, or pardon me, principled, we now can do it smaller. We can report smaller or larger values. Depending if it's going from larger to smaller, smaller to larger, we can do signed or absolute, and we can do curvature, direction, or vector. So now we can actually see the potential direction of of the curvature of your object, and from there you can create some really cool vectors to do some really interesting things. For instance, on terrain, you can actually get a director in which the curvature is flowing, and on characters you can actually see the direction in which the surface is flowing. Really, really cool tool that way. And so I think I got some, yeah, there we go. And the next thing is, oh, I got a really cool file on I won't go in there. It's going to take too long. Some other nodes in here. So fuse and measure are the two really, really big ones that I'm really enjoying, and I'll cover the RBDs in a bit later. But another one is height field cutout by object. I'm sort of sweeping the whole terrain options into a single node, which it essentially is. So what this allows us to do now is, we have an issue with volume, with terrains. I think that's an issue that's generic to the entire industry, where if you have very large terrain tiles, like 8x8 or 12x12K, dealing with all that massive volume data is very difficult. And a lot of mobile games, they approach that by doing hex tiles for their games. So we have a really cool way of providing, being able to do what's called height field cut by object. And I'm going to take a look quickly at what that workflow can look like. And while that's going, I'll take a look at a couple more of these options that we have here. So you can see some example files. And what this allows us to do now, this is a very low resolution height field, but we can use cut by object, and you can see how the edges are much sharper than what the volume is actually at. So it gives us the ability now. And also when you render with Mantra and you convert it to polygons, we keep that silhouette. And the one thing to note with height field by volume is when we do cut it out, the memory is still used for the remainder of the tile, but it's not considered to be active. So by putting things in the tile that are visible or invisible with this new alpha channel, it allows us to consider where we want to do work and where we don't want to do work. In this particular example, we actually just take a standard height field with some noise on it, and then over here we just have a hex tile shape. We just create a grid of hex tiles, and then we simply then we poly extrude them, and then we just simply cut up by object. So so the height field cut up by object is really easy. You take your terrain field, you put in your manifold geometry, and then it just cuts it out. And now when we run the noise is only considered where the height fields are. The memory is still consumed by the files, but they're not considered in terms of evaluation, so it's pretty good. And when we convert the height field to polygons, as I said before, we now keep the silhouette edges. So there you go. Really cool tool. And let's go back up. So lots of modified suits. I'm going to cover more as time goes on, but the bounce up, actually I do have to cover this one. This one is hugely important. So a lot of the new fracturing workflows, we know, I showed this like 6-7 years ago, where one of the main ways to do fracturing is you take a look at a very complex object, and then you calculate its favorite face, and then you move that to the origin facing you, and then you shatter it, and then you move it back. And in 17.5, we now finally have a really great way of representing that inside of Houdini. And so we have, did I close the wrong one? Nope. And so that's coming up. So we have a really great way of representing that now. And I'll show you that. It's a really simple example. And this is also a way that I highly recommend everybody uses Houdini. I think all the old school users do this anyway. Don't bite everything off at the same time. And when I'm looking at something new, so basically what I want to do is I want to take Flippy. I want to fracture him into many different pieces. And basically and so he's comprised of many different features, many different pieces. And what I want to do is I want to shatter each piece at the origin in a particular direction. So what I can do is I can assemble this fractured object. Let's say it's coming in from another application, or Alembic or whatever. And I can use the assemble. And the assemble, what it does is it constructs a name attribute. And that name attribute I can now use to blast. In this case, I just blast one little piece. I don't know, by group 1. I can choose any group I want. And just by using the middle mouse slider. And let's say it's that piece now. I unpack it. And then I create so the new SOP is the bound SOP. And what it can do is it creates this transform attribute. And the transform attribute, and it also I've got turned on orientated bounding box. So you can see the orientated bounding box is set. And what transform by attribute means, it actually calculates the transform. And now I can actually do the transform by attribute SOP, which has an invert, and it works directly with this matrix. And so now I can move this object to the origin. I can move the bounding box to the origin. I can then do a Voronoi fracture, and then I can transform by attribute back again. So that's my first test. Okay, fine, I can move a box. Then I need to do that on the geometry itself. So we have actually, attribute transfer has two inputs. The second input is the object that I can transform. Transform by attribute now works on the piece that I'm working. And then I do a Voronoi fracture on that, and then I transfer it back. So now that I know that I got this going, I can know Houdini. I go straight to a compile block and a for each block. And easy. Once you do these compile blocks a couple times, it's really, so basically I took that routine and then I just literally copied and pasted inside of this for each block. You can actually see there's my primitive SOP, there's my transform by attribute, there's my bound SOP. So basically it's in there. The guts are still there, and then when we do that, and I wrap it inside of a compile block because all those nodes are safe, and now I can actually shatter this piece of geometry however I want. And what's nice about this is I can put whatever I want in here. As we know with Houdini, I can then put, let's put a sphere in here, try a sphere, polygon sphere, pretty boring, but anyway, you can see how that will work. So now we've got a universal system that allows us to shatter anything however we want. And every piece is going to be put at the proper origin to shattering. Great for doing wood. And guess what? We are using these techniques to do some wood shattering as well, as a matter of fact. So that's good. So this file will be made available, obviously. So, and let's go back up. And I know my time, right?
Do you want to have 10 minutes for Q&A?
Yeah. So I'm going to wrap. So I'm going to rip through the last few. So bullet improvements. We got lots of really cool bullet improvements. The three main things are constraint from lines, constraint from rules, and constraint from curves. So let's have a shot at constraint from curves, first of all. So I would say that the new RBD constraints inside of 17.0, great first pass. Still some problems with constraints, not really user accessible, and so 17.5 we addressed the ability to grab constraints and actually work with them. So what I'm going to do is put down a box and dive inside, and this box, I'm going to move it up. And as we all know, the primitives are now, all our primitives now have rotates on them, so that'll be great because I'm going to rotate this guy, something like that, a bit more. And so I'm going to do this one, and let's do that, and let's rotate it a bit like that. And I'm going to actually fracture this, material fracture, RBD material fracture. And when it comes, and I can do that, and I'm happy, and now I can pack this. So why the RBD pack? I'll show you in a minute. We can actually build systems. Let's say we're building a building and it's got all kinds of pieces to it. We can take those models and then we can build into it these material fractures and actually add into it everything that you need in a single input. So that now allows me to, for instance, just let's just grab a copy of this. And while it's cooking, I can now take this box and I can move it up a bit. And of course I'm looking through the material fracture and I can template that guy. And just because I want to get them pretty close. Okay. Now in the first box though, I want to do some more work to them. So in here we now have a new tool called the RBD fracture, what is it? RBD constraint from, let's do curves. And now this gives me the ability, now this is that state tool. Remember I talked to you about the Python state? This is actually a Python state. And you can see at the bottom we actually have some text. So if I shift left drag, I can actually draw my curve that I want to create my constraints from. And if I go to the RBD material fracture, oh, that's my time. If I go to the RBD material fracture, I can then go here and yeah, so I'm just going to actually add some more fracturing. So scatter points are going to go to 10. And so I do that, and now I can constraint him. And look at that, now I pack him up. It's got both constraints in there. And then finally down here, I can actually put down another RBD constraints from, let's do another constraints from curves. And I can drag and drop that into there. And now I can actually hit escape and then enter in there. And now move my display flag there, that's right. And now I can draw another line in here. So if I hold the shift key And I can start drawing another line. And you can see here there's all kinds of options to middle to tweak points, so I can actually middle to tweak these various points and I can move them around. There's ways of getting handles, and we're constantly refining this user workflow. But the nice thing about it now is because we're using a state, if you want a request for this change to the functionality, you can go right into the Python code or you can request it from side effects, and we no longer have to go back to the developer and dirty the node, right? So we just modify the state. There's no need to recreate the digital asset or create a new version. And now the last thing I'm going to do now is I'm going to do a merge. So now we can build building components, right? We can have roof structures, we can have, I said merge. And we can build all these different pieces of our building and do all the fracturing in place. But what do we do to glue all the pieces together? Now I'm going to do an RBD unpack. And this is one of the last things you will do, is we can now use the third one, which is RBD constraints from rules. And RBD constraints from rules is our procedural Ginsu knife to actually constrain everything together. You can already see it automatically created these constraint primitives to glue these two pieces together. And now let's add a collision plane. And let's take these boxes. I'm just going to go here and go to rigid bodies, rigid body objects, select my objects, hit enter, and press forward. And now you can see some of the pieces are constrained together. So really easy to do these sorts of work. I think we recorded the video that we did in Munich. We go in a bit more detail into this as well, so definitely check that out. There's a lot of promise in here to work inside of Houdini. Now the final feature that I got is the PDG, and then I'll take questions, which is like the one that's unbounded. The PDG deserves an hour in itself. Let's just put it out that way. But I thought I'd just do a really, really basic PDG graph, and then I'll take lots of questions. The number one thing you're going to be using with PDG is the number one problem we have with newer users. Many, many times I get asked, you might have a very, very sophisticated simulation artist coming from another application, and they still can't get their head around that Houdini is actually a framework and can put nodes in multiple directories. They're used to a very flat world. So one of the things that PDG allows us to do is coalesce all of those output drivers into a single location. And it truly, in this particular case, it truly is a fantastic replacement for ROPS. So I'm just going to put a sphere down. I'm going to put a pyro solver down here, so pyro effects. Let's put billowy smoke. And in the billowy smoke, play forward, everything's fine. But the problem we want to do is we have to cache this to disk. And the way we cache these things to disk is we normally have to go to ROPS and put that down, or many times inside of these nodes, there'll be placeholders where we can actually dump stuff out. For instance, we have import pyro fields for visualization, and we have the actual fields that get used for rendering in the import pyro fields. So that's for visualization. And we got a whole bunch of volumes in there, but it actually has in its save to file. So you're poking through your file and doing it, what's updated, what's not. So we now have, why did I do that? Unlock, sorry about that. And now I just need to put a top graph. And this completely replaces ROPS. I can put in here, and I can put down ROP geometry output. And I can point it at just the SOP that I want. So just like you do with ROPS and TOPS, I can actually grab now, it was the import pyro fields, I can just drag and drop it into there. And when I do that, I can actually, this is this new context that we call tasks, right? And I right mouse on this, I can actually say dirty and cook the selected node. And I can see that I got one task ready to go. And what is that task? If I middle mouse on this, it tells me that it's a top net geometry, and it's only a single frame. So let's actually give it a frame range. And in this case, I'm going to delete this channel, set it to, let's say, 20. And now I recook this, so I dirty and cook selected node, and now you can see there's all my 20 different, it's now running the simulation. And I can keep on working. Let's put down a top. Let's put down, in this case, I now want to do a render, so I'm going to put down a mantra ROP. ROP mantra render, and I just keep on going. So now everything that is in TOPS, I can now schedule this inside of here. And I can say that's good enough, and now I can right mouse on this, and then I can say cook selected node. And now what it's going to do is for every task that's coming in, it's now going to generate a render task. And because the rendering is, it's sequential, but in this case it doesn't matter. This mantra ROP is just going to fire as many tasks as it can to work and go forward. So you just keep on, and if you have more outputs to cache, you can add them beside and merge them together. There's lots of videos on TOPS to get going as well, and to work forward. But I highly recommend reading the first the first PDF that was done by Rob McGee with help from R&D and an intern that was really good. I highly recommend you go through this, create a task workflow to build cities. It's quite a complicated file, but what it is that you learn inside of this is the ability to take any geometry, process each piece, and use and schedule the way to build a large terrain, whereby if I just make a change on a single building, only that building will evaluate. And it covers all kinds of really cool tricks, such as using a ROP output driver set to not use local SOP to dive inside of there and actually build some geometry and work forward that way. So lots of other stuff that we can look at PDG. I think we're going to save it for an Illum. I think we really want to do a whole bunch of things on pipeline. I really want to tackle pipeline, final once and for all. I've seen so many pipelines in my day, and I got a good inkling as to what works and what doesn't, and so you can sort of decompose pipelines and rebuild them up from scratch, see where scripts can go in the eyes of a PDG, because the PDG really can map and control an entire pipeline, or just do some image conversion or whatever. So it's pretty amazing. So I guess I'd open the field to questions.
Unfortunately, we don't have time anymore.
No, we got 5 minutes. Oh, okay.
But Jeff will be around, so if you have questions, I'm sure you can catch him, and then he'll